Hey everyone, and welcome to this explainer. Today we're going to unpack one of the absolute most fascinating environmental detective stories of the 20th century. You know, if you were around in the 1970s and 80s, you probably remember the sheer panic surrounding acid rain. I mean, it literally felt like an apocalyptic threat, like the world was just dissolving from the sky down. But honestly, what's so incredible about this story isn't just the massive scale of the disaster. It's how science, economics, and policy actually came together and solved it. It's a real triumph. So we're going to look at the mechanics behind the mess, some really weird geographic mysteries, and the brilliant market-based solution that essentially caught and neutralized our culprit. Let's get right into it.
Okay, let's dive into this global crime scene. Picture this. On one side of the world, the intricate, super durable marble of the Taj Mahal and even ancient European Gothic cathedrals are quite literally dissolving. They're just losing these beautiful surface details they'd held onto for centuries. Then, on the totally opposite side of the world, in the Adirondack Mountains of New York, hundreds of pristine, beautiful lakes are suddenly just lifeless, completely fishless, entire aquatic ecosystems collapsing overnight. So what on earth was the invisible killer connecting eroding ancient statues in the city to dying fish in an isolated mountain lake?
To figure that out, we first need to establish a scientific baseline. Now, you might be surprised to learn that normal rain is actually already a tiny bit acidic. Because atmospheric carbon dioxide naturally dissolves into rainwater, it forms this very weak carbonic acid, bringing normal rain to a pH of about 5.6. But the precipitation falling over the northeastern US and parts of Europe during the peak of this crisis, totally different story. We officially define acid rain as precipitation with a pH below 5.0. And historically, back in the 1970s and 80s, we were seeing rain with pH values plummeting to 4.2 or even 4.4. And because the pH scale is logarithmic, that is exponentially more acidic than natural rain. It's like vinegar falling from the sky. So where was all this highly destructive acid actually coming from?
Well, the culprit was a process formerly known as acid deposition. Basically, this is the transfer of atmospheric acids, specifically sulfuric acid and nitric acid, down to the Earth's surface. And this actually happens in two ways. There's wet deposition, which is your acid rain, snow, or fog, and then there's dry deposition, where dry acidic particles and gases just absorb directly onto surfaces. But here's the absolute crucial part of this whole thing: the transport disconnect. See, the bulk of this pollution, primarily sulfur dioxide, was being pumped out by coal-burning power plants over in the Ohio Valley. But atmospheric winds picked up those pollutants and transported them hundreds of miles away. They ended up falling as acid on the forests of New England. This massive disconnect, where the source of the pollution and the actual geographic victims were totally separate, created an absolute nightmare for both ecologists and politicians.
So how exactly does coal smoke turn into an acid bath in the atmosphere? It's kind of an invisible chemistry pathway. Step 1. Sulfur dioxide, or SO2 gas, is released from those smokestacks and eventually drifts up and enters the cloud water in the atmosphere. Step 2. Once it's in that watery aqueous phase inside the cloud, the dissolved SO2 reacts with other chemicals floating around up there, like hydrogen peroxide or ozone. Step 3. This reaction forces the gas to fundamentally transform into sulfuric acid, which fully breaks apart in the cloud droplet. So by the time that droplet finally falls as rain or snow, it's carrying a heavy, dangerous load of acidity straight down to the ground.
And you know, it wasn't always just a slow, steady, year-round drizzle of acid doing the damage. Oh no. In places with seasonal snowpacks, we saw this really visceral, devastating phenomenon called the spring acid pulse. Basically, throughout the long winter, all those acidic pollutants would just accumulate and build up in the snowpack. So when spring finally hit and the snow melted, it unleashed all of that stored up acid in one massive, concentrated burst. This highly toxic pulse would surge right into lakes and streams at the exact critical time of year when vulnerable amphibian populations were trying to breed and sensitive fish eggs were hatching. It would literally wipe out entire generations of aquatic life in just a matter of days. Heartbreaking, really.
The sheer variety of destruction this acid caused across completely different environments is staggering. Let's break it down. First, lakes and streams. When the pH drops below 5.0, seminides, think brook trout and Atlantic salmon, they suffer terribly. The proteins in their gills actually denature, meaning they break down in the acid, completely destroying their ability to breathe and regulate ions. Moving to forests. Acid rain burns leaves directly, sure, but worse, it acidifies the actual soil. This makes aluminum, which is just naturally sitting inert in the dirt, become soluble and highly toxic to tree roots. It also washes away vital nutrients like calcium. This exact soil chemistry is what caused those massive, famous forest diebacks in Germany's Black Forest and the Appalachian spruce fir forests. And finally, buildings.
Sulfuric acid reacts directly with carbonate stones like limestone and marble. It converts hard, ancient, super durable calcite into soft, water-soluble gypsum. And then, that soft gypsum literally just washes away in the next rainstorm. But right about here is where our detective story takes a really fascinating turn. As scientists were tracking all this widespread destruction, they stumbled onto a glaring geographical mystery. Why did the lakes in the Northeast, like up in the Adirondacks, completely die off, while lakes over in the Midwest totally survived? I mean, the Midwestern lakes were exposed to the exact same, or sometimes even higher, levels of acid rain coming from those nearby power plants. So what exactly was acting as a shield for the Midwest?
Well, the answer lies in nature's own armor, something called buffer capacity. Put simply, buffer capacity is a watershed's ability to take a hit of incoming acidity and neutralize it without experiencing a massive drop in its overall pH. You can think of it as basically an ecosystem's built-in antacid. And whether or not an ecosystem has this antacid entirely depends on the geologic bedrock buried deep beneath the soil.
So it really just came down to a geologic lottery. The Adirondacks, the Catskills, the Canadian Shield up in the Northeast, they're all sitting on top of ancient granite and quartz-like silicious rocks. And those rocks, they have absolutely zero carbonate buffering capacity. Nothing. They were completely defenseless when the acid rain hit. But the Midwest, its bedrock is packed with limestone and carbonate minerals. When acidic water hits limestone, it dissolves the carbonate, which releases bicarbonate and hydroxide ions. These ions essentially neutralize the acid safely, right there in the ground, before it can ever reach the surface waters. So the geography of this disaster wasn't just about where the wind blew the smoke, it was literally about the chemical composition of the ground itself.
Section 1. The hero of the story. The 1990 cap-and-trade solution. Let's look at how we fixed this.
To actually solve this massive crisis, policymakers tried something entirely unprecedented in U.S. environmental law. Instead of using top-down regulation to order every single plant to install the exact same expensive technology, they introduced a market-based mechanism. Here's how it worked. First, the EPA set a strict, non-negotiable national cap, a ceiling on total sulfur dioxide emissions. Then power plants were handed a limited number of allowances, with one allowance permitting exactly 1 ton of SO2 emissions. But here is the genius part. They could trade them. If a plant figured out a really cheap way to install pollution controls, they could reduce their emissions way below their limit and then sell their leftover, surplus allowances for a profit to another plant where upgrading was just too expensive. And to force continuous progress, the overall national cap was designed to fall over time. This made the allowances scarcer, inherently more valuable, and progressively tightened the economic vice to clean up the air. And the results of this policy? Staggering. Absolutely staggering. We are not talking about a modest little improvement here. This is arguably the most compelling, quantifiable success story in all of U.S. environmental policy. By 2020, sulfur dioxide emissions from U.S. power plants had plummeted by approximately 88% from their 1990 levels. That massive drop beat virtually every single projection made back in the 90s. And because the free market naturally hunted down the absolute cheapest ways to reduce emissions, whether through trading, switching fuels, or targeted scrubber installations, the overall economic cost to the energy industry was a fraction of what anyone anticipated. Today, because of this exact mechanism, lakes in the Adirondacks are literally recovering. Life is returning.
Now, naturally, looking at this huge home run, people always ask, well, if cap-and-trade worked so perfectly for acid rain, why is there so much political gridlock when we try to apply it to global climate change and CO2? Well, the conditions are just fundamentally different. The SO2 program worked beautifully because the pollution sources were a highly locatable, specific industry, all operating within a single U.S. jurisdiction. Plus, the victims, the dead lakes, the dying forests, they were a very visible, very politically legible constituency. CO2, however, is what economists call a global public bad, a shared negative consequence that affects literally everyone on Earth. There's no single national cap that can fully capture this global externality, that hidden cost to society that simply isn't reflected in the price of fossil fuels. The political economy surrounding carbon is vastly more entrenched and complex, and the sources of CO2, they're everywhere. So while the economic math behind cap-and-trade remains completely sound, the political and geographic realities we're dealing with today are a totally different beast.
Which really leaves us with this final, crucial question to ponder. We know for a fact that when science identifies an invisible atmospheric threat and policy actively aligns market incentives to target that exact threat, we can pull massive ecosystems right back from the brink. The great mystery of acid rain was solved, and the culprit was successfully neutralized. But as we face the infinitely more complex global climate crisis today, the question isn't whether we have the right economic tools in our belt. We know we do. The real question is,
Can we somehow replicate the political will and those perfectly aligned conditions of the 1990s to save our ecosystems on a global scale? Definitely something to think about. Thank you so much for joining me for this explainer, and keep exploring the science.